to speak about the pH-zone refining CCC. So why the pH-zone refining CCC called the efficient preparative separation method for natural product? Because this method can purify the gram quantity of the pure natural product during the one-step separation from the crude extractors. So this, I'm going to skip the few slides because the other speaker already talked a lot about this project. So I don't want to spend too much time on here. So CCC, I like the Dr. Juice compare the CCC. He described CCC as a bicycle, he said. Also, if HPLC like a car, we don't want to competing with HPLC in the highway, you know. But in the world, you have a lot of narrow road, so car never can reach. So CCC is maybe the best way, the bicycle maybe the best way to get some small road. So also, like the natural product, is CCC is the best way, maybe not the best way, but it's a very good way to handle the dirty crude extract from the natural product. So I think the CCC have it all advantages compared with HPLC. So this is the instrument. Is a prototype instrument developed by Dr. Ito in his lab. I think a lot of commercial companies copied this model and they have a lot of commercial and available now. In this, okay. So this instrument contains the 3 multi-coil columns. You can see from here, this is one column, this is another one is on the back, one is rotated. So this column can hold about 1.6 liter total capacity. So, but this column can be changeable. You can make the smaller amount too. You use a different size of tube. So most of the separation I'm going to introduce here is use this instrument. So this is a G-type motion for the CCC. I don't want to talk about anymore about this. Dr. Conway have a nice model showed you last time how this motion works. So I just want to say this, like this is a J-type anti-twisting design. So Dr. Conway also demonstrated this with the dancing with Dr. Leto. You can see how it can be works. The mechanism is very simple. But this design, you know, Dr. Ito have almost 100 patents. His patent resulting about more than 10 commercial CCC instruments. But none of this instrument has been making money for NIH or even for himself. But this design was used for the blood separation. This was because for the old design of the blood separation, they use the rotating seal. You know, the rotating seal is a very expensive device. You cannot discard it for each people, one-time user. So they use this design for the blood separation. You can, when you donate blood, the partially donate the blood, you can use one tubing of the centrifuge. They take out the parts they want. Other parts can be sent back to your body. But you don't want to use a rotating seal with this device. This causes cross contamination. So they use Dr. Ito's this anti-twisting design for this blood separator. So this because this is a large scale, lot of use for in the world. So it makes millions of dollars for NIH. Also, Dr. Ito also got some profit for it too. So that is the only case one that I cannot say the only one, but that patent make some profit. So okay, I want to escape this slide because Dr. Conway showed use his model. Also, Alan showed the movie how this works. I don't want to speak more here. So then we go back to the pH-zone refining CCC. So in this part, I'm going to talking about how this method was found, also the mechanism, and the most important part, I will give a lot of examples for its applications. So this is experiment did by Dr. Ito in his lab. So he found the first slide in this chromatogram. He found unusual sharp peak after he purified the two compounds. This is a bromine acetic T3 is a kind of dye, is acetic dye. So this compound, this is the impurity. He found the peak eluted late is much sharper than the peak eluted earlier. This is unusual for the CCC chromatography. Most of the chromatography should be early peak is sharp, late peak should be border. So in this one, he calculated the theoretical plate. First peak is like 800, is normal for regular CCC, but the later peak is about 2000. It's very unusual for CCC, for this peak. Then he tried another solvent system in this chromatogram. And this chromatograph, both the retention phase became a little bit more polar. So both the peak was eluted a little bit later, it's delayed. So he found this sharp peak was switched. The first peak became sharp. The second peak became broad. So what does this mean? That means this sharp peak caused is not because of the sample itself. It's because something else may be present in the sample solution. So he further studied this, then finally found he measured the pH of each collected fraction. He found a very, very interesting way. We can see this line. This is the pH. He found the pH is gradually dropped. After the solvent front came out, the pH was gradually dropped. Then it was suddenly goes up during the sharp peak area. That means the sample solution must be contains something. Then he analyzed the early fraction by mass spectrum. He found that early fraction contains bromine acetic acid. That is acid was appeared there. So because the sharp change of the pH caused that sharp peak formed. So then he finally found the theory how this peak was formed. Because the sample solution contains the acid, when you elute it with the mobile phase is relatively basic, then it will be form a sharp border of the acetic border, like showed here. This border. This is a stationary phase, is a mobile phase. When the stationary phase was moving, it has a relatively basic condition. Then because the analyzer, so after because the upper phase, let me get. here is a is acidic condition. This is the basic condition. When the mobile phase was moving forward, it will be switched a little bit, then became the analyzer is an acidic compound. It will move down to the basic, because it became ionized, then they go to the aqueous phase. When this ionized analyzer was moving forward, then reach the acidic border, then it will be protonated, then go to the upper phase. So it will be form a circle during this sharp acidic zone. So it will, if this analyzer can form this circle during the acidic zone, they will be form a sharp peak. So otherwise, it will have a normal bald peak. So he further studied this method. He added three acetic acid during the stationary phase. He called this three acid the spacer acid. One is the acetic acid, one is the proponic acid, and butyric acid. This three acid was added in the sample solution, and these three DNP amino acid, because we block this is blocked the N-terminal of amino acid, so it's acetic compound for three. After eluted with aqueous solvent, he found first acetic acid will be eluted out because this most acid compare this have lowest pKa. Acetic acid will be eluted first, then form a 1 pH zone. Then the proponic acid will be eluted, form a second pH zone. Then last one is the butyric acid eluted. After this, then go to the normal mobile phase pH. So during each of these zones changes, all the three analyzed. This one pKa is between these two acids. Then it will be eluted as a sharp peak during the sharp change of this pH zone. This compound pKa is between these two acids, so it will be eluted between this pH zone. The final one is pKa is bigger than butyric acid. It will be eluted last at this zone. So this is he called the peak sharpening technique. But this technique is useful to make the peak sharp. But more important application he was found later in here. When he increased the sample size, the previous slide we can see the sharp peak. The sample size is 6 milligram of each analyte. In here, he increased the sample size 100 times to 600 milligrams. He found it very interesting. This sharp peak became a sharp rectangular peak between these three spacer acids. All these three analytes became a sharp rectangular peak. Also, this each rectangular peak have its own pH zone. So when he take out the other two spacer acids, only keep the one acetic acid, then these three peaks will be eluted together as a rectangular peak with a very sharp border. When you see the pH zone, this zone is still keep same as before, but these three compounds will have its own pH zone. So this can be completely separated. So now I'm going to explain why this form this sharp pH zone. This is how the solvent system was prepared for this pH zone refining CCC. We make a two-phase solvent system. Here we use ether as an organic phase. You can use any other solvent too. So you make a two-phase solvent system. After separate this two-phase solvent system, you separate the upper phase and the lower phase and put in different container. Then for the stationary phase, in here we use organic phase as a stationary phase. We add the TFA as a retainer acid. So we use aqueous phase as a mobile phase. We add the ammonia as a elute base. So in this case, the column, HPLC column, will be first. Oh, sorry. More. So in here, the column will be first filled with the stationary phase, contains the retainer acid. Then after sample was injected, this will be eluted with the mobile phase, contains the ammonia as a elute base. So after the equilibrium was formed, the first retainer acid will be formed a sharp pH zone, will be moved consistently from starting point to the from head to tail. So when this sharp border was moving, the second lowest pKa compound will be form a pH zone eluted immediately after this retainer acid. The iron circle is as showed before. It will, during each border, it will be form iron circle. So the second low pKa compound will be eluted next to this one. Then the low, not low, the second high pKa compound. This is the highest pKa compound will be eluted last. Then all those pH zones will move in constantly pass through the column. After elute, you will get this chromatogram. After the solvent front, this zone is formed by the retainer acid. This is a TFA zone. So after TFA was eluted, this is the sharp zone for the retainer acid. Then the first lowest pKa compound is eluted out. Then it will be form a plateau is consistent pH zone, because this zone is determined by the concentration of the base, eluted base in the mobile phase. So this concentration, this concentration for this zone is the same as the concentration of the compound you add in the mobile phase, the basic eluted base you add in the mobile phase. So it forms these three compounds. It forms three zones. Each compound has its own pH, special pH, during this solvent system. So this method is a separated compound. This separation factor is determined by two factors. We know normal CCC separation factor is mostly determined by the partition coefficient between the two-phase solvent system. In here, now the partition coefficient is also important, but in here another factor was also in fact this separation is the pKa. So pH-zone refining CCC actually they use two separation factors. One is the partition coefficient, one is the pKa, the compound pKa itself. So we come to the interesting application of this method. The first slide shows the separation of acetic dye. This dye, they call Orange 5, is FDA approved compound. FDA approved dye can be added to the food. So actually this dye is not a single compound, it's a mixture of these three compounds, three acids. We can say that structure is very similar. So this is the HPLC. We can say these three peaks. After purified by pH-zone refining CCC, this is a 10 gram the sample. I think it's 10 gram. I will check. 10 gram, maybe 5 gram. I will check more. Then this uses a normal 300 milliliter CCC. So we can see each compound form this is the pH, this is the UV, this big rectangular peak is the UV, this step-by-step one is the pH zone. In this study, actually we measured the pH by each cubes. You also can use the online flow-through pH meter to measure this pH. So for each zone, we analyzed the fraction by HPLC. You can see this each zone is a pure compound. So the small impurities was focused on the border of this zone. Oh yeah, that was 5 grams. This chromatogram is the same as the previous one. We can, in here, I want to show the pH-zone refining CCC can handle the different size of samples. This first one is 350 milligrams, 1 gram, 5 grams. So with the increase of the sample size, the mixing zone for each is almost the same, but the pure fraction of this pH plateau is getting broader. That means with the increase of the sample size, the sample, you get the more purified sample because the mixing zone is almost similar. So you increasing size, the sample yield getting higher. This is one of the good advantages for pH-zone refining CCC method. They like to handle the larger scale samples. So we can say the most commercial available CCC, they have upper limit. They give the upper limit of the sample scale. So the most of this record was made by this method. When the pH-zone refining CCC was found, the first was found for the separation of the acetic compound. Then we think this method can also be applied for separation of basic compound, especially the alkaloid from natural product. Then when we presented this idea to Dr. Ito's boss, Hank Fields, he was a natural product chemist 20 years ago. He have a lot of natural product crude samples. Then he found a sample, he said, contains these three alkaloids. from his old box maybe about 20 years ago. He used. Then we use this pH-zone refining CCC. We use, in this case, we also use the organic phase as a stationary phase in this chromatogram. So we add the retainer base, not the retainer acid. If you separate acetic compound, you add the retainer acid. In here, we add the retainer base. We use the triisoamine as a retainer base in this case, and eluted with hydrochloric acid. So we can say this can be clearly separated into 3 zones, 3 pH zones. Then we analyze each zone, we get this pure fractions of these 3 compounds. Also, we can find, because this is use aqueous phase as a mobile phase, it's similar like the HPLC, reverse phase HPLC, so we call this reverse displacement model. And so in this case, we use the aqueous phase as a stationary phase, eluted with organic phase. So in here, when the fraction was eluted as a salt, alkaloid fraction was eluted as salt. In here, the up phase is the mobile phase, so we got the free base alkaloid. So you have a choice for these 2 methods, depend on how you want this your compound. You want the salt, you can use the aqueous phase as a mobile phase. If you want the free base, you can use the organic phase as a mobile phase. Also, it's because some alkaloid is stable in salt, you want to use this method. If it's stable in free base, you want to use this method. So you have choice to select the mobile phase. This is the application for separation of the modified peptide. We block the one side, the N side of the tripeptide. Then this will become a free acid. The one side have a free acid. So this peptide, protected peptide, can be separated by pH-zone refining CCC. We can say this, each peptide have its own pH plateau. This is a partition coefficient without the acid and base. We can say this 2 was switched. According to normal CCC, this one may, according to this partition coefficient, this peak may eluted earlier. But in the pH-zone refining CCC, here the pKa may be more important. Here, this peak will be eluted earlier, so it switched. But we can see the both factor will affect this separation. So we know sometimes only the partition coefficient is not enough to separate the compound, especially for this catecholamine compound. This compound is very polar. In most of the solvent system, it will be mostly partitioned into the aqueous phase. So in this case, we add an affinity ligand into the stationary phase. So we can see the first chromatogram, if no affinity ligand, all these peaks eluted in the one peak. After you add this affinity ligand, all this catecholamine can be completely separated. So we also can apply this affinity ligand in pH-zone refining CCC. In this case, the pH-zone refining CCC, the separation factor will be determined by 3 factors. First is the hydrophobicity. One is pKa, then is the affinity to the special ligand. This is the separation of this catecholamine by pH-zone refining CCC and the affinity ligand. We can see all this peak was clearly separated with its all pH zone. CCC method to separate the free peptide is also challenging because most of the peptides also is they have a very similar polarity, so it's very hard to select the solvent system to separate all different kind of peptide mixture. So in here, we add the affinity ligand in the stationary phase. Use the pH-zone refining CCC to separate the free peptide. We can see this is a group of hydrophilic peptide. This can be clearly separated for this. This is only the model for simple peptide. This is a hydrophobic peptide. We can see all these four peptides can be clearly resolved. We use this method to separate some natural peptide too. It's very useful. We can get like a 10 grams quality, 10 grams sample add to the regular semi-preparative CCC column. It get very good result. I didn't bring the example for here, so. And this one is a chiral separation. We can add the chiral selector in the CCC stationary phase. This is the 4 pair of the chiral compound. After add this is no chiral selector. After add the chiral selector, we can see this 4 pair of the chiral compound was clearly separated. This is we call the chiral CCC. So we also can apply the chiral selector for the pH zone refining separation. This slide showed we separate the DNB leucine. It's enantiomers for 2 grams of mixture of enantiomers for this compound. So we add the retainer acid and the chiral selector into a stationary phase, eluted with ammonia. We can see even these enantiomers can form this all pH zone with the help of the chiral selector. So this is analytical CCC to detect the purification of each pH. We can see this each plot is clearly separated. This is this one, this is this one, and this is the mixing room. So they go back to the CCC, the pH zone refining CCC separation of the natural product. This natural product, this is the lignan. So this compound is the weak acid because it have a phenyl group. In this case, if low the eluted base, if you only use the ammonia, they cannot partition this compound to the aqueous phase. You have to use sodium hydroxide as a elute base. Sodium hydroxide can be make the phenyl compound ionized to go to the lower phase. This is where this compound was extracted from a plant from Africa. So Dr. Huang's group in Johns Hopkins, they found this compound have a very good anti-HIV activity. So we can see here, we can get 2 pH-zone. One zone we got NDGA. This is all this group is hydroxy. Another zone is a mixture of the 3-methyl and the 4-methyl. This here, because this maybe this pK is too close, hydrophobicity also is too close. We cannot completely separate these two, but we can. These two compounds can be from the same plateau. Can be the mixture eluted from here. So this is a larger scale separation of that same crude extract. This is our story for this compound, because a pharmaceutical company want to test the clinical trial for this. I think the 4-methyl NDGA. They need 10 grams of pure compound. So that time, Dr. Ju from Pharmatech Technology, he got this contract. They gave him like kilograms of crude extract. They want him to get the 10 grams of pure 4-methyl NDGA during the 1 month. Because he saw we had been applied, we had been separated this compound use the pH-zone refining CCC. So he think that job should be easily done. He charged the company the small amount of money. Then after I talked with him, he really realized how hard this project could be, because this kilogram quantity of crude extract, you get 10 grams of pure natural product during 1 month. But finally, he used his largest scale CCC developed in his lab. It's 800 milliliter per the capacity. So that time, I don't know that Dr. Sutherland have that big instrument. So finally, we found that 800 instrument use the pH-zone refining CCC. They can handle the 20 gram to 50 grams crude extractions. So after the separation, we can see this have 2 clearly plateaus. One is NDGA, one is 3,4-methyl NDGA. This is a mixture. We have to collect these fractions and then separate these two by normal CCC. This is a good example for combine the pH-zone refining CCC and the normal preparative CCC. So after purified this 3,4-methyl compound, we found we got a lot of side product of NDGA. This is all the hydroxy. The only difference is 1-methyl difference. So we decided to put this NDGA, methylize this NDGA, use a chemical reaction. This is a product after the chemical methylization for the NDGA, we separated this reaction mixture. We also get these 4 pH plateaus. One is unreacted NDGA, that's a small amount. Mostly is a mixture of 3 or 4 methyl NDGA. We also have a little bit overreacted dimethyl NDGA compound. So this provides another way to get the 4-methyl NDGA. So this is a larger scale separation compared with the previous slide. Okay, this is another application of the pH-zone refining CCC for alkaloid. This work was did in Dr. Yang in Beijing New Technology Institute. He also put a different size of the crude extraction, did the pH-zone refining CCC. He found after increase the sample size, he got another plateau. The major compound in his extraction, I think he already, his crude extract already processed after some kind of processing. It's not directly crude extraction, but it's also in mixture with something. So he got the major product is the first compound, this compound. So after increase the sample size, he got another zone, pure zone for the second compound. Also, he collected the mixing boulder. He separated another two. So in this case, the pH-zone refining CCC, in large scale, he can get two pure alkaloids. From the mixing zone, he got the actual compound. So actually, for the natural product studies, this mixing zone is also very important because the pH-zone refining CCC can concentrate the small amount compound during this pH zone. So if you want to find some real compound, maybe the new structures or some new activities, this mixing zone may be very important for the research studies. So this is another example for the alkaloid from natural product. So this is we can see this two compound structure is very close. It can be clearly separated during the pH-zone refining CCC. It have its own pH zone. This is the pure fraction. This is the pure fraction. So this is also recently publication from one group. So I think okay, the different structure difference here have a double bond here and that. So we can say these two also can be clearly separated by this pH-zone refining method. Okay, this is a sample from the fungals. So this is Dr. Gay Harris' work in the Merck. So we can say this compound didn't have much UV absorbance. So the UV detector is very hard to detect them. But we can use the pH zone to detect this. This is after the separation, he analyzed this fraction by HPLC, then he got the figure of this one. But actually, this is not UV absorbance. So this is his HPLC fraction. He draws these peaks. We can see these three compounds is clearly separated, detected by this pH zone. This is these three compounds. You can see the structure is very close. This is a very good example for the use pH zone refining CCC in natural product separation. Okay, this is a list for the recently publication for the natural product. We list the samples, how much the sample scale, also the two-phase solvent system you can use for the different kind of compound. They have alkaloid, peptide, polyphenols, carbohydroxide acid, and other compound too. We can see they have a lot of examples, solvent system to be choose. Here, the most solvent system choose the use MBE. I think we can use all the other solvent system too. Why they use all use MBE? Because maybe the early publication of the pH-zone refining CCC use the MBE. But I think this method can use all the solvent system. The key of this system, when you select the solvent system, you will be tested in the acidic condition. If your compound is alkaloid, so if you test it in the acidic condition, most compounds should go to the lower phase. In the basic condition, most compounds go to the upper phase. If that works, then I think pH-zone refining CCC, that solvent system should be works too. So this is a list of the retainer base and the retainer acid. Actually, the key of this one is we want this retainer base or retainer acid most partitioned in your organic stationary phase. So it's why we use triisoamine and TFA. You can use other too. But the key of this separation is your retainer acid must be stronger acid than the acetic compound you want to separate it. If you use a basic compound, this retainer base should be stronger than your samples. That means that the pK should be bigger than your sample. So this is the eluted acid or eluted base. This depends on your compound. If they can ionize in your case, for example, for the normal carbohydroxide compound, you can use ammonia to be ionized in the lower phase. But for the phenol compound, you have to use a stronger base like a sodium hydroxide. So we go to the conclusion. First, pH-zone refining CCC can make the sample loading capacity increase over 10 times. We already see a lot of examples for this method. This is a great advantage for this method because we can use the regular CCC column to do the large-scale preparative separation. So the fractions are highly concentrated. This is very easy to understand. We can see all the diluted peak became saturated. We diluted as a rectangular peak. Also, this concentration is determined by the elution base concentration of the elution base and the elution acid. So base acid. So I think the highest concentration can be go if it's not saturated from your solvent system. Sometimes if you put too concentrated, the salt will be precipitated. That is not good for your separation. So you can adjust this. Also depend on your sample size. If your sample size is relatively smaller, I recommend use a little bit low concentration. You can get the bolder, the fraction, the pH zone is a little bit longer. You can get a more clearly separated fraction during the middle of the zone. So if your sample size is large, so you better use a little bit high concentration elute base, so elute acid or elute base. So it depends on your fraction. It depends on your sample size. So yield is improved by increase the sample size. This can be understood by use example I first gave, because the mixing room for the different size of different scale separation is almost kept same. So after you increase in sample size, your pure room is getting broader, so you get more pure compound. So these minor impurities are concentrated and detected and peak border. So this is, I already said, this is very important for the natural product research. So elution peak can be monitored with a pH flow meter without the chromatograph. So that is another advantage. Okay, thank you for your attention.